Have you ever just stopped and stared at a massive modern manufacturing plant? The sheer synchronization of all that incredibly complex equipment almost looks like magic. But actually, it's a highly orchestrated, lightning-fast conversation. Welcome to This Explainer. Today, we're going to uncover the hidden language of automated factories. We are diving into the fundamentals of industrial signal types, which is basically the invisible nervous system that keeps our entire modern world running.
So, the absolutely crucial question we need to start with is, how do these machines actually talk to each other? I mean, think about it. When a huge industrial tank is getting way too full, how exactly does it tell the pump to slow down? Well, they obviously don't use words. Instead, they rely on a highly specific vocabulary of instrumentation signals. These signals are quite literally the lifeblood of automation. They translate physical realities, things like pressure, temperature, and speed, into pure data that a central computer can understand. And then it turns that computer's decisions right back into physical actions. Okay, let's dive into this and look at the actual alphabet they use.
Section 1. Analog versus digital signals, the Great Divide. To really understand this language, we first have to look at its two main dialects. Over on the analog side, things are continuous. Imagine a proportional control valve adjusting a fluid flow to, say, 10%, then 45%, or maybe 99%. It represents a constantly varying physical condition. It's smooth. Now, contrast that with digital signals. Digital signals are sharp, they're definitive, and rhythmic. Strictly on or off, a 0 or a 1. There's zero in between here. It's kind of the difference between asking, hey, exactly how fast are you going, versus asking, is the engine running at all? Both are completely vital, but they serve completely different purposes on the factory floor.
All right, moving on to Section 2, the Core 4 signals.
To build our vocabulary, we really have to think of the central controller, which we usually call a PLC, or programmable logic controller, as the brain of the whole operation. It's constantly listening, and it's constantly speaking. Inputs are what the machine hears or feels from the outside world. Outputs, those are the commands the brain shouts back out to make things happen. When we cross-reference those inputs and outputs with analog and digital, we get the absolute core acronyms of industrial automation: AI, AO, DI, and DO. Honestly, if you understand these four concepts, you pretty much understand the foundational language of almost every automated process on Earth. Let's break them down one by one.
First up is the analog input, or AI. This is a continuous signal flowing from a field device straight into the controller. Now, the most common standard you're going to see out in the field is a 4 to 20 milliamp electrical current, or sometimes a 0 to 10 volt signal. Imagine a temperature sensor tucked inside a massive industrial baking oven. As that oven heats up, the electrical current smoothly rises from 4 milliamps all the way up to 20 milliamps. The controller is constantly listening to this flow of electricity, so it instantly knows exactly how hot the oven is at any given millisecond.
Next, we've got the analog output, or AO. This is just the reverse. It's the continuous signal being sent from the controller out to a physical device. Let's say our controller decides that the oven we just talked about is getting a little too hot. Well, it doesn't just want to slam the gas line shut entirely, right? Instead, it sends out a varying analog output signal to a control valve, smoothly twisting it partially closed just to reduce the flame a bit. You'll also see AOs used to send speed commands to a VFD, that's a variable frequency drive, smoothly spinning a motor up or down rather than just aggressively jerking it on and off. Okay, let's shift gears to the digital side of things and see how this fills out our vocabulary. A digital input, or DI, is entirely different from its analog cousin. This is a snappy, definitive on or off signal coming into the controller. No gray areas here whatsoever. It comes from devices like simple switches, proximity sensors, or feedback contacts. Picture a fast-moving conveyor belt. A box slides down the belt, it hits a physical limit switch, and bam, a digital input fires right into the controller. The message is incredibly simple and binary. The box is here. Finally, to complete our core 4, we have the digital output, or DO. This is the decisive, absolutely uncompromising on or off command sent from the controller out to the real world. When the controller processes that a dangerous pressure limit has been reached, it is definitely not sending a gentle analog suggestion. No, it fires a digital output to instantly trip a relay, blast an emergency alarm, pop a solenoid, or just completely kill a motor. It's literally the controller shouting, "Do this action right now." Section 3, other common signal types, the alternative dialects.
So while those core 4 electrical signals make up the vast majority of our industrial vocabulary, there are absolutely some alternative regional dialects out there on the factory floor.
First, we have pneumatic signals. I always find this one pretty fascinating because the machines are literally using pressurized air to talk to each other. The industry standard here is 3 to 15 psi of air pressure. If a valve needs to open, the controller quite literally blows compressed air down a tube to physically push it open. Then we have hydraulic signals. These take a much slicker, definitely heavier duty approach by transferring oil pressure through the system for just incredible raw power. Digging just a little deeper into the other two dialects, we have pulse or frequency signals and smart signals. Pulse signals are essentially fast-paced digital clicks used as counters. If you need to measure the exact RPM of a spinning turbine, or say, measure the flow of water rushing through a pipe, a sensor will send a rapid-fire sequence of pulses that the controller counts up to determine the speed. Then we have smart, or digital communication signals. This is where things get really advanced. Instead of just a simple voltage, these use complex digital protocols like HART, Modbus, or Profibus to send whole data packets. A smart signal doesn't just tell the controller the temperature. It can basically say, hey, here's the temperature, and oh, by the way, my internal battery is running low, so I'm going to need maintenance next Tuesday. It provides incredibly deep machine diagnostics.
Section 4. Putting it all together. A complete conversation.
It's really crucial to realize that without these signals acting in perfect harmony, the modern manufacturing, water treatment, and power generation facilities we absolutely rely on would just instantly halt. Let's walk through a perfect, simple example from our source material that beautifully illustrates a complete sentence in machine language. So, step 1, we have a pressure transmitter on a pipeline. It measures the pressure and sends a continuous 4 to 20 milliamp signal. That's our analog input back to the PLC. Step 2, the PLC, our brain, receives that AI, processes the logic, and realizes, the pressure is dropping too low. Step 3, the PLC immediately responds by sending out its own continuous 4 to 20 milliamp signal, an analog output, straight to a control valve, telling it to open up just a little bit more to restore that pressure. Input, process, output. It is just a continuous, flawless loop of communication, keeping the whole system perfectly balanced.
And that brings us to the end of our explainer. It really kind of changes the way you look at industrial automation, doesn't it? It's not just a bunch of dumb metal banging together. It's this highly sophisticated network of continuous and binary data, of electrical currents and compressed air, constantly chatting back and forth. So I'll leave you with this provocative thought. Next time you see a factory, or even just drive past a manufacturing plant on the highway, ask yourself, beneath all that noise and the steam, what are the machines whispering to each other right now? Thanks for joining me on this deep dive into industrial signal types. Keep learning and stay curious.